In this video, I will present the Fourier Transform, starting out with very basic concepts and then leading all the way to deriving all of the expressions, all of the equations in Fourier Analysis and Fourier Synthesis. This is really important to understand for signal and image processing, as well as many other fields, including quantum mechanics. So to start off with, I'll use a very simple example, that of food. On the left-hand side, I've got a pancake. And here I'm presenting the concept of analysis. We can look at what are the ingredients inside this pancake. So for example, here I've got various ingredients, flour, milk and salt, with differing amounts. So that is the result of an analysis of the ingredients of a pancake. When I've got those ingredients, if you like the decomposition of that pancake, I can then do a synthesis. With this list of ingredients of varying amounts, I can recombine them and then form, create, reconstruct, synthesize a pancake. So a very simple concept. We can extend it to the example of chemistry. Common salt, for example, we know that's sodium chloride. If we did a chemical analysis of that, we would see that it's 1 part sodium, 1 part chlorine. When we know that, we're able to do a chemical synthesis and actually create salt. So now we'll look at the particular example of functions such as an audio signal, a sound recording, for example. So here we've got a recording, a function. This is like an amplitude of the audio signal f, which varies with time. So time is that horizontal axis. We can likewise, just like we saw with the food example and the chemistry example, we can do an analysis. In this case, we're going to analyze that signal in terms of its frequency content. So what does that look like? So just here are a few examples of different frequency components. Here I've got high frequencies at the top, lower frequencies at the bottom, and then I'm looking at a various amount A. So you can see here I've got different amounts. We'll see what that amount corresponds to in a moment, of a different frequency omega. So omega here is low and high at the top. When we've got that analysis, we could represent it like this, where we've got some amount or amplitude of a particular frequency omega plotted as some function here. And we'll see more examples of this as we go along. When we've got that analysis in terms of the frequency components that are present in that signal, we can do a synthesis of those frequencies. What that means is adding together these components, these different frequency components with different amounts, different amplitudes, combining them together, or indeed summing them together. That's why we use an integral sign here. An elongated S for summation. We can sum over all the frequencies. Here I'm using d omega to reflect the fact that in fact we could have a whole continuous variation in frequencies from low to high. I'm just showing you a few examples on the screen here. We can sum all those frequency components together to do a synthesis to re-obtain the signal f of t. Now, the benefit of doing that analysis, just like with the food example and the chemistry example, was to understand the contents of that signal in a way that is useful to us. Also, though, we could process the signal far more easily when we've got this kind of frequency-based description. So, for example, with an audio signal, I could emphasize bass low frequencies, or I could reduce high frequencies that might correspond to noise, and I can do that processing very simply on this, this frequency description here. And then when I've done my processing, I can then do a synthesis to rebuild or reconstruct either the original function if I've done no processing, or indeed a processed version of that signal. The same concept applies to that of 2D images. So here I've got a simple photograph on the left-hand side. Imagine that in grayscale for simplicity. And I'm showing here, and we'll do an animation in a moment to demonstrate this even more clearly, I'm showing here that I could do an analysis of the various two-dimensional frequency components that make up that photograph. So I'm only showing a limited example subset here. There'll be many more frequencies involved. And just also show here the relation with the previous examples I've been showing. I could do a profile through one of these 2D frequency components, and I would get one of those frequencies that we've seen in the 1D example earlier. We'll go into this in more detail in the coming slides, but again, just conveying the concept here. And then when we've got those frequencies, we could weight them with differing amounts, different amplitudes, add them all together. That's the synthesis approach, where we can then re-obtain the original image. Or indeed, if we wanted to do some kind of processing in this frequency domain, What we could do, for example, is remove some of those more detailed higher frequency components and then do the synthesis. And if we do that, we see here we've now blurred the image by removal of those high frequency components. So these are just conceptual examples. Let's move on to an example, an animation now. So I'm showing here another photograph on the left-hand side here. And then what I'm showing here, courtesy of this animation from Tyler Moore, is all the different 2D frequency components. You can see them all there animated that would be contained within that photograph. And here we have the amplitudes now on a grid. Instead of that 1D function A of omega, here we are now building up a 2D grid which are coefficients, the amounts for each of those frequencies that you just saw in that animation. And if we were to use those amplitudes with those frequency components, we could rebuild or synthesize the signal, in this case a 2D image, as I'm showing on the right-hand side of the slide here. So here you can see that I'm adding together more and more of those high frequency components. We'll see frequency in more detail in a moment, but you can see by adding them together we eventually are able to synthesize that original 2D photograph. Okay, let's go back to the 1D case from here on to make it really clear. So remember then, we've got some signal, some function of time. We can do an analysis into different frequency components. There are, in general, infinitely many, but when we sample, we have a limited number of frequencies, and there are differing amounts of each of those frequency components, and we can represent it such as in this graph here, a certain amount of a particular frequency omega. Here I'm just showing 4 example frequencies that might be present in differing amounts. And then when we've got that, as mentioned, we can synthesize the signal. Okay, now let's take a look at what I mean by the amount of a particular frequency. By the amount, I'm really referring to the amplitude of a frequency component. So here I'm showing an amplitude of 3, just as an arbitrary example, for frequency omega is equal to 1. So what that means is that amplitude there, if you like, is 3 multiplied by this basic building block, the cosine function. Then as we increase the amount of frequency omega is equal to 1, that corresponds to increasing the amplitude. So you can see here, I've got an example of amplitude 4, and here an example of amplitude 5. And you can see that what that's done is just kind of stretch that cosine function, just scale it upwards, just increase the amplitude of it. Or indeed, I could scale it down. Here I've just got amplitude of 1 on that cosine function. So that explains the concept of the amount or the amplitude of a frequency component. Now, in terms of frequency itself, what do we mean by that? So here I'm showing the case of omega is equal to 1 again. And what that means is that I've just got one waveform within some interval or some distance. So here I'm using a distance or interval of 2 pi because that will simplify the equations that will come later on. Now, as I increase frequency, that corresponds to fitting more of those waveforms within that interval 2 pi. So for example, here I've got 2 waveforms, here 3 waveforms fitting in within some interval 2 pi, and I've got 6 waveforms in that case there. Or indeed, I've got the special case of the 0 frequency where I have no waveforms, it's just a constant function. Then of course I could combine both concepts of varying the amplitude, varying the amount, as well as varying the frequency. So, for example, I could take 2 lots of the 0 frequency, 4 lots of the first frequency, and varying amounts of the other frequencies, and that would give me an amount A of frequency omega, which traces out in general some function. Remember here, I'm only showing a discrete number of frequencies, but in this graph, I'm showing that in fact, we could have a whole continuous variation in the frequencies, as well as continuous variation in the amplitude for each of those frequencies. And then when I've got the analysis, the Fourier analysis, as we'll see, a function such as this, I can then use that to synthesize, to rebuild a function by adding together those frequency components with their respective amplitudes. So here's a nice graphical example of some function of time, and you can see here in blue the frequency components that are going into making up that red function f of t. So here now we'll visualize that red function f of t and show that it's actually composed of different frequencies of different amplitudes. And it's the amount of each of those frequencies that is, if you like, the Fourier analysis. In other words, how much of each frequency omega is present in that original function f of t. So this is where we're up to now then. We've got some function of time. We're doing an analysis of the frequencies to say how much is present of each frequency in that function. Then once we've got that information, of course we could process it, we could modify it, but in general here, just to understand Fourier analysis, what we're going to be doing is just resynthesizing, rebuilding the function. So let's take a look now at some of the equations here. So I'm saying I've got some frequency component cos omega t. So here I've got changing omega, as we've seen before. And now I'm saying I can just scale that by an amount or an amplitude a, which depends on the particular frequency omega. Then I need to sum, that's the integral sign for summation, over all the frequencies omega. So imagine a whole continuous range of frequencies that I'm summing over, add them all together with their various coefficients, or indeed their amplitudes a as a function of omega. Then I just need to scale, because I'm using omega in terms of the number of waveforms fitting in 2 pi, it means I just need to put a scale factor in the front there. It simplifies the mathematics later on when we get to the Fourier transform. And so I'm saying this synthesis is therefore just the summation of cosine frequency components, giving me the original function f of t. So at this point, I'll quickly show one more example using a MATLAB demo here. Here I've got a 2D test object often used in medical imaging. And what I've done is I've just taken a 1D profile, just a line profile through the center of that test object. And I'm just plotting that here as another example of an arbitrary function that we could synthesize by adding together various frequency components. So what I'm going to show now is an addition of cosine functions as well as sine functions, and we'll see why in a few moments' time, why we need the sine functions as well. So here now I'm taking cosine functions of increasing frequency as well as sine functions of increasing frequency. I'm adding them together with certain scaling factors, certain amounts or coefficients to recreate or to synthesize that original function. So I've got this Fourier synthesis. You can see it's being composed of the cosine and the sine, with various amounts a, an amount a for the cosine, and we'll see later an amount b for the sine. When we use those respective amounts, you can see here I've got a perfect reconstruction of that original arbitrary function f of x. Here it was just a profile for an image, and I've got no error at all in my Fourier synthesis. So I hope by this point in the presentation you're now convinced that we can add together frequencies with varying amounts to reconstruct functions, whether in 1D or in 2D. I've been focusing more recently here on 1D. But the question that should really be in your minds by this point is, well, how do we go about finding how much, in other words, how much of each frequency component do we need in order to reconstruct or synthesize a function or a signal? So that's what I'm going to be covering next. So here again is my f of t, function of time, and what we're presupposing is, and hopefully graphically demonstrated sufficiently already, is we're saying that function of time is actually composed of really a nearly infinite number of frequency components. I'm just showing 4 example cosine frequency components here that could be present in f of t. And we're saying that these are variously weighted, so there'd be a of 0 plus a of 1, a of 2, a of 3, various amounts of each of those cosines present in f of t. But how do we find what a of omega is for a given function f of t? So let's take a look at how we can do that. It actually turns out to be a very, very simple process. So in forming this function, you've got to imagine we're wanting to find a, the amount a of a particular frequency omega, as we progress along that frequency axis, the omega axis. We're trying to find how much of each frequency is present in f of t. So for simplicity here, I'll say, well, imagine I'm trying to find the value of a for omega is equal to 1. Well, we know for omega is equal to 1, that would be a cosine of just one waveform fitting in 2 pi. So how do we find out how much of that is present in our example function f of t? Well, all we have to do, as it turns out, is simply take the function that we want to decompose into all these various frequency components, and we just multiply it by the frequency component that we wish to find the amplitude for, or the coefficient for. So let's see how this can possibly work. So what we're saying is f of t is composed of all these frequency components. We just multiply f of t by a particular choice of frequency. Okay, we're trying to find a for a particular choice of frequency. Here I'm giving the demo of omega is equal to 1 waveform in 2 pi. I just multiply that by f of t, and what we see is if we just consider that that f of t does indeed, we assume it does contain cos 1t in it, and of course that first frequency. Assuming that is present, if it isn't present, this would just be 0, but assuming it is present, when we multiply this by this cosine function, we end up with a cosine squared. And notice a cosine squared function is a purely positive function. So if we integrate it, we will get a finite result. And in particular, we'll get a finite result that's actually proportional to the amplitude or the amount of that frequency that is present in f of t. So to get the amount of a particular frequency, all I do is multiply f of t by that particular frequency and then integrate. And that will give me the amount of that frequency present in f of t. It is that simple. But perhaps you might be wondering, well, hang on a minute, aren't there many frequencies contained within f of t? So how does this manage to only give the amount of a particular frequency omega in f of t? What about the other frequencies? Well, let's take a look at what happens if we multiply cos omega t by any other case of a different omega value. So let's take a look, for example, if we were to multiply this cos omega is equal to 1t, if we multiply that by, for example, the 0 frequency component that is present in f of t, look at what happens. We just get a cosine function that's as much positive as it is negative. So if we integrate that, we will get a 0 result. So when we're looking to find the amount of cos omega t that's present in f of t, it will only give us the amount of that frequency present and won't give us the amount, for example, of the 0 frequency that's present, because that gives a 0 result, and it's only squared when it meets itself in the function. So let's do one more demonstration of that. So in the next example now, I'm showing what happens again if we just fix on this omega equals 1 case, multiply it now by this other second frequency component that is present in f of t. And again, what we see is when you multiply cos of 1 by cos of 2, you end up with a function that's as much positive as it is negative. So if you integrate that, you get a 0 result. And in fact, the same would be true for all the other frequency components, which means, due to the remarkable property of orthogonality of cosine functions, whenever we do this process, we'll only be picking out uniquely the amount of each frequency component omega as we do this integral equation. In other words, you take the function, multiply it by the frequency that you want to find out about in terms of how much is present in the signal, multiply it, and then integrate, and that will give you just the amount of that particular frequency that is present. Okay, so let's now get the mathematics sorted for this. What we're saying is, in summary, we've got f of t now being analysed into some amount a for frequency omega. We know from before that we can write down the synthesis expression here, saying f of t is just a summation of cosine frequencies with varying amounts a of omega. And now what we've seen is, to find those amounts of particular frequencies omega, all we do is take f of t, multiply it by the frequency for which we wish to find the coefficient, or for which we wish to find the amount a, and integrate. And that will give us the analysis, the Fourier analysis, albeit in this initial case just for cosines. But now the point is, we need to deal with more general functions. We can't just get away with only a non-shifted cosine, because our functions could be differently positioned in time. And so to be more general, we're going to need to consider the fact that those cosine functions could be differently positioned with some phase shift to capture all kinds of arbitrary functions here. And that phase shift, that sliding to the left or right of each frequency component, that phase shift will also depend on the frequency itself. So I'm crudely animating here the fact that those frequencies could slide to the left or right, but the amount of sliding could change according to the particular frequency. So let's now develop our mathematics from those previous slides to now accommodate for this more general, fully general case actually. So first of all, I'm going to make use of a well-known trig expression, which is cos of this difference of two arguments, difference of angles if you like, is just given by a cos with no shift added to a sine with no shift, where you just have a scaling factor in front of the cosine and the sine that depends on that shift component. And so we're going to make use of that and say, well, actually, our cosine with a phase shift is none other than a cosine with no phase shift added to a sine with no phase shift, where all that matters is the relative amounts, here I'm calling them A and B, the relative amounts of a cosine and sine will give you a cosine with just a different shift according to the relative amounts of A and B. So a cosine with any shift is just equal to a sum of a cosine with no shift and a sine with no shift. So we're going to make use of this now to be able to generalize the mathematics that we've developed thus far. Okay, so here we are again with our 1D function being analysed into certain amounts of each frequency component, the cosine frequencies, and we know we can do the synthesis of that function. And in fact, this would only be true if this is a real even function, but where we're going now by adding on the sines is to make this true for any real valued function. We know that we can do the synthesis here by summing over all the cosine frequencies with various amounts A, and we'd have found those various amounts A just by doing this simplistic multiplication and integration. But we've got to build in the sine component now as well in order to account for any phase shift of those cosines. So here I'm showing differing amounts of the sine function. So I'm going to say A is the amount of the cosine of a particular frequency omega, and I'm going to use capital B for the amount of each sine of a particular frequency omega. So that means we can extend now the synthesis expression to now add on the fact that it's not only a cosine of a particular coefficient or amount A, but also add on the sine omega with a particular amount B, which also depends on omega. So that's the more general synthesis expression for a real valued function. And the argument should be straightforward to follow from the previous slides, that just like for the cosine component, we can find A of omega just by doing this product and integration. Likewise, we can find the amount B of sine omega t just by multiplying sine omega t by the function and integrating. Beautifully simple, because sine and cosine are orthogonal functions. Okay, and then also we'll not forget to put in that scale factor multiplying by 1 over 2 pi. Right, so this is our rather kind of clumsy looking synthesis expression now for any real valued function. It doesn't have to be periodic because we're having continuously varying frequencies here. And what we're going to do now is develop this into a more compact and a more contemporary notation. So my first step is going to be to use Euler's relation for cosine and for sine. If I do that, we know that cosine can be written as the sum of two complex exponentials, where we now have a positive argument and a negative argument for the complex coefficient. For the complex exponential is what I meant. And then for the sine, again, we can now write that as a difference of two complex exponentials. So this is looking worse at this stage, but if you were to follow through the mathematics, which I won't do extensively in this presentation, but just to point out that if you work this through, then you can actually combine A and B into one single complex entity, a complex number f, which depends on frequency omega. Now notice in this example, I'm dealing with a real valued function f of t, but I'm now, by use of Euler's expression, building in complex numbers, but I've still got a real valued function on the left-hand side here. So please do not lose sight of that. Complex numbers here have come in just as mathematical convenience for what we're about to do. Because if we define this by grouping the terms here, we can end up with a beautifully compact expression, which is our Fourier synthesis. And in fact, for this general case now, where we've got the sine and the cosine, combining them with into a complex exponential. This is known as the inverse Fourier transform. And so that, I hope, is recognizable to you. And notice that, again, this is true for a real valued function on the left-hand side, but also, actually, as it turns out, this is also true for complex valued functions f as well. So a very useful expression there. Right, so let's see where that takes us now in terms of our analysis expressions. So we remember that this f of omega, the amount of a particular frequency omega that is present, where now omega is that complex exponential made up of sine and cosine, as we know by Euler's expression. We know it's just given by the summation of those two analysis expressions, and we know from our previous slides, this is the analysis for the cosine, this is like a cosine transform, this is the analysis for the sine, this is like a sine transform. Then what we can do is just work through the mathematics very simply. We just substitute these two expressions into that expression there, and so then we can get an expression for the amount, the complex valued amount f of the frequency omega, as just given by that straightforward expression, just by substituting in. And then if we work that through, this is immediately recognizable as the Fourier transform, because Euler's expression says that e to the minus I omega t is going to be cos omega t minus I sine omega t. Sine is an odd function, cos is an even function. And so this is now the very well-known expression for the Fourier transform, and I hope you've been convinced that this is now directly relatable to real valued functions, as I've been demonstrating at length. So in summary then, this is the Fourier transform expression here, f of omega. This just gives us the amount of frequency omega that is present in f of t, where the frequency omega really is e to the plus I omega t. Okay, and so the reason that's the case, and the reason the analysis uses the negative, is because this is trying to pick out the e to the plus I omega t that is assumed present in f of t. So when this meets its counterpart in f of t, we'd get e to the plus I omega t multiplied by e to the minus I omega t, which is e to the 0 value of 1, which is finite on integration. Hence that gives us the amount, that complex valued amount or complex coefficient f for frequency omega. So that's the Fourier transform. And then the Fourier synthesis is just the inverse Fourier transform. We're saying take that amount of frequency omega, there is the amount f of frequency omega, use that as a coefficient, if you like, or a scaling factor for the complex exponential. That's just your cos and sine that we've seen before already. Sum over all of the frequencies, do the scaling, because I'm using omega, I'm using an interval of 2 pi for the definitions of my frequencies, and that will actually synthesize the original function f of t. So just to finish then with another graphical example, there's an f of t, and I'm just showing that that can be composed of differing amounts, shown in blue, of all of those different frequency components, that when you add them all together, when you synthesize them, you can arrive at reconstructing or synthesizing some function. And so there, f of omega, that sinc function there, is in fact the Fourier transform of that top hat function that we just saw. So I'll just finish then with the summary slide summarizing both the Fourier transform and the inverse Fourier transform. Thanks for listening.